Imagine stepping into a video game to battle an army of monsters. Your job? Summon your own army to meet them on the field and neutralize this invasion. The battle strategy is to balance numbers so your army is just large enough to take out theirs. Neutralization is the key. Just like in this game, chemistry has its own battles, where acids and bases clash until only the largest army still has combatants on the field. Let's find out more. This is Real Chem. Neutralization in chemistry mirrors the strategy of balancing forces. When acids and bases meet, it's like two powerful armies colliding. But instead of chaos, their interaction creates harmony, destroying the combatants and leaving behind water and salt. The neutralization process is fundamental to understanding pH and reactions in real-world applications. Today, we'll explore how acids and bases neutralize each other and how this balance shapes the chemistry around us. Picture two opposing armies: strong acid monsters, hydronium ions, and strong base monsters, hydroxide ions, ready to clash. Each has a unique attack. Acids bring water molecules with an extra proton, forming hydronium, while bases bring water molecules missing a proton, forming hydroxide. When hydronium and hydroxide meet, proton transfer occurs, neutralizing them into two water molecules that merge with the surrounding aqueous solution. The monsters also bring along their fans. Consider hydrochloric acid, HCl, and sodium hydroxide, NaOH. In an aqueous solution, HCl becomes a positive hydronium ion and a negative chloride ion. The aqueous NaOH becomes a negative hydroxide ion and a positive sodium ion. The only job of the chloride and sodium is to keep the solution electrically neutral. We call them spectator ions because they just watch from the sidelines as the hydronium ion and hydroxide ions fight it out. When the battle between one HCl unit and one NaOH unit is done, the two ions have neutralized each other, forming a water molecule that fades into the aqueous solution. This leaves only the spectator ions, sodium and chloride, floating freely into the water. In our battle rules for chemistry, one hydronium ion and one hydroxide ion neutralize each other. You can't have large amounts of both present because they will attack each other until one of the combatants is no longer a majority species. The larger army always wins. If the acid army is bigger, excess acid is left after the battle, and the resulting solution has an acidic pH less than 7. If the base army is bigger, excess base is left after the battle, and the resulting solution has a basic pH greater than 7. The math associated with the battle is that of limiting reagents. The smaller army is the limiting reagent and is completely destroyed, leaving the excess reagent as the majority species. Let's say we have initial concentrations of 0.5 molar HCl and 0.4 molar NaOH. Our acid has the larger army of hydronium with H3O plus equals 0.5 molar compared to the base's hydroxide ion concentration of OH minus equals 0.4 molar. Each hydroxide ion is destroyed by a hydronium ion for a change in concentration of 0.4 molar for each combatant. Once the battle is over, our only remaining majority species is hydronium ion with a concentration of 0.1 molar. We have assumed that the neutralization reaction goes to completion, or K goes to infinity. But remember, K is large, not infinite. Therefore, the hydroxide ion concentration is small, but not zero. It is the minority species. We can now determine its true concentration. We know the hydronium ion concentration is 0.1 molar. Therefore, the pH is negative log of 0.1 or a pH of 1. We also know that pH plus pOH equals 14. Since pH is 1, pOH equals 13. This corresponds to a hydroxide concentration of 10 to the negative 13. Let's flip the match. This time, our initial concentrations are OH minus equals 0.6 molar and H plus equals 0.5 molar. When the battle is over, we have hydroxide, the majority species, with a concentration of 0.1 molar. This corresponds to a pOH of 1. The minority species is now hydronium. We can determine its concentration from either the Kw expression, giving us 10 to the minus 13 molar, or the sum of pH and pOH being 14, giving us pH equals 13. It may seem odd that even in basic solutions where hydronium ions are present at much lower concentrations than hydroxide, we typically report pH instead of pOH. This convention is useful because it provides a single consistent scale, the pH scale, for both acidic and basic solution. Today we uncovered how acids and bases neutralize each other like opposing monster forces in a video game. Get the numbers right and you balance the forces. By carefully balancing hydronium and hydroxide ions through processes such as titration, we achieve harmony, leaving water and salt behind. Whether it's the acid or the base that starts stronger, the ultimate goal is balance, a concept at the heart of chemistry.